I'm Jörg Böckelmann. I'm one of the persons here in the Max Perutz Climate Initiative. We are a group of committed individuals, and next to tackling the plastic waste problem and just analyzing the data here on the campus, we have this lecture series, and every couple of weeks we have different talks to different topics. And I'm happy to announce today's talk. It's about the impact, mainly the energy and the water consumption of the cloud computing. And we invited David Mytton, and he's not just a developer on his own with a company providing tools for developers. He's also a researcher and related to the Uptime Institute and the Imperial College. And he even published some papers on exactly the topic today's talk is about. And there will be time for questions at the end. Otherwise, you can just type them in the chat in between. This talk will be recorded and is later also available on our YouTube channel. David, really thank you very much for doing this for us, and we are all looking forward to this talk. It's yours now. Thanks a lot.
Thank you. Hello, everybody. Let me share my screen. So you should see there's the slides there now. Just move this out of the way. All right, so I'm going to be talking to you about energy and water consumption in IT, primarily focusing on energy, but water is directly linked to the energy consumption of data centers. Now, my day job is in running a software startup. I've been doing this for over 15 years. I've run and sold a couple of different companies over the last few years, but have also been researching in energy technologies and energy policy at Imperial College London and specializing in sustainable computing, and also working with the Uptime Institute, who are a global advisory group who work with all of the major computing companies to help them design and build data centers. And I'm on the data center environmental sustainability team. Now, the first question is really simple. It's what is a data center? These are huge warehouses that exist all over the world, but they can actually be any size. And just like when you're using an application on your phone or your laptop, whenever you use the internet, those applications, documents, videos, they all need to be located on a computer. And these computers are known as servers. And they are just like your computer, except they don't have a keyboard or screen. And they need to be somewhere with a really good internet connection, where they have access to power, and they can be kept cool. And this is essentially what a data center is. This photo shows a Google data center in the US, and you can see the rows of racks of servers where they're all stacked together. And they can range in size from small 100 square foot cabinets all the way up to 400,000 square foot, what are known as hyperscale warehouse facilities. Essentially, whenever you're accessing something on the internet, you're connecting to at least one of many hundreds of thousands of servers that are located inside one of the many thousands of data centers all around the world. Now, a major component of the environmental impact of a data center is the electricity needed to power those servers. But there are several components that I'll go through which contribute to the overall footprint. Now, the first of these is the servers I was just talking about, and these are essentially where all the processing happens. It's the CPU itself, the processor, and also the memory. And power draw for these components is partially related to usage, but certainly historically, they can be very inefficient, drawing up to 70% of their total maximum power, even when doing absolutely nothing. Now, over time, changes in hardware and the software on the management system has improved this figure, but despite this, servers still rarely run at full utilization, and the most efficient tend to run at only 50% utilization. There are a number of reasons for this. The first is that software is just not that efficient, just because the capability of hardware has increased massively over the last couple of decades. And maybe 20 or 30 years ago, programmers were struggling or had to put a lot of effort into optimizing their software to make best use of the resources available. The capabilities of modern processors and modern computers just far outweighs the processing needs for most workloads. But then the other reason for not going above 50% utilization is reliability and failover, and just having the additional capacity to be able to deal with the loss of a server for critical workloads. Now in 2010, the global installed server stock was estimated around 35 million servers, but that's expected to grow to over 57 million by the end of 2023. And that's growing at around 8% per year. However, the majority of that growth is going to come from the hyperscale cloud providers. And whereas they were estimated to be responsible for just 8% of servers in 2010, estimates suggest that by 2023, that could be over 56%. That's quite a significant growth. And when I'm talking about hyperscale, I mean Amazon Web Services, Google Cloud, and Microsoft Azure. However, there are some indications that that growth may not reach such high levels, and I'll come on to that in a few minutes. Now, the second component is storage. And this photo shows a robot that is moving around to access disks that's installed in another Google data center in the US. And you can see that from the stats, 2018, it's over 1,000 exabytes across a 250 million drives have been installed. And those are consuming around 23 terawatt hours of installed capacity. The power draw for drives varies depending on the drive type, whether it's a hard disk or a solid state drive, but it's typically between 6 and 7 or thereabouts watts per drive. The efficiency of these is improving quite significantly. The overall wattage is decreasing by about 5% each year. So whilst the amount of storage space is increasing and the number of drives is increasing, the total power draw that's expected by 2023 is actually going to be lower than where we were at a couple of years ago. And this is because of the improved efficiency. But if you just think about all of the data that's being uploaded to just YouTube, but all the photos that everyone's taking, or the documents that are being posted, you can understand why the number of drives is increasing significantly. Networking is another component. This is the third component. And there are varying estimates for the energy intensity of the internet. And these range quite significantly by multiple orders of magnitude, ranging from 136 kilowatt hours per gigabyte in 2000 to 0.004 kilowatt hours per gigabyte in 2008. But when you get into the details, start analyzing the calculation methodologies, the generally accepted figure for 2015 is 0.06 kilowatt hours per gigabyte. And this is decreasing by about 50% every 2 years. It's actually been quite challenging to find good quality literature on this topic because of the different methodologies that are used, but also the different system boundaries. And this estimate is only looking at fixed line telecoms in developed countries. And we know that mobile traffic is growing significantly, almost 50% every single year, and it's going to make up 20% of all internet traffic by 2022. But we don't have any really robust analysis of the energy intensity of mobile connectivity. And this is particularly a problem because of how rapidly the technologies change. Just a couple of years ago, we were all connecting using 3G. 4G connectivity is the most common today, but there are already devices on the market, including from the leading manufacturers like the iPhone, which are moving to 5G. And there just isn't any assessment available that allows us to understand the true energy consumption of these new technologies. And this is a challenge, particularly in developing countries where, whilst over the last 100 years certainly in Europe and the US, we've gone gradually to all the different technologies and people tend to have fixed lines at home. In countries like Southeast Asia and certainly in Africa, a large part of that infrastructure is just going to be skipped. and people are going to go direct to mobile connectivity. And then this also excludes all the internal traffic. So within data centers, those servers are talking to each other, even if there's no data going outside of the data center. And there's generally no literature on understanding that kind of energy intensity, looking at all the internal network switches and all of the cabling and how much energy that uses. But stats from Facebook show that that traffic is doubling every 12 to 15 months. And so it's really quite difficult to understand the true energy impact of networking. And then we come to the data center building itself. And this is infrastructure that supports all the servers, disks, and networking that is stored within it. It includes cooling, power distribution, backup batteries and generators, lighting, fire suppression, and then the building materials themselves. Now, the industry uses a common metric called power usage effectiveness, or PUE. This is a ratio between power drawn by the infrastructure components to the power delivered to the servers, disks, and networking equipment. And the ideal value for this is 1.0, which means that 100% of the power that goes into the data center goes to the IT equipment. But larger data centers tend to have lower PUE ratios, which usually means that they're more efficient. However, using PUE alone has been criticized because it can be lower when IT load increases. So it makes it a useful metric to understand efficiency improvements within the data center, and is often used to compare between data centers, although it wasn't designed for that, but it doesn't necessarily indicate efficiency by itself. Now, of course, a PUE of 1.0 is essentially impossible, because if 100% of the power is going to the IT equipment, then that would ignore any losses or the cooling and would mean you wouldn't need a building at all. So this is a theoretical ideal value and is generally not reached at all anywhere. And indeed, the industry average is about 1.67. Every year, Uptime Institute surveys all its members and get reports of what the PUE values are across a wide range of different types of data centers. And you can see here it's been falling, certainly in the beginning of the early 2000s, but we've started to reach a potential plateau of the limits to which efficiency can be improved inside existing buildings that haven't necessarily been designed with efficiency in mind. However, the large hyperscalers are pushing these limits, and Google is one of the few, or it's the only one of the three that publishes its PUE values for the facilities that it owns on a quarterly basis. And you can see here that they've been pushing down not just the quarterly PUE, which changes depending on the season and the specific location of the data center, but also looking at their trailing 12-month average across their entire fleet. And pushing this down to 1.09, 1.10 is about getting to the limits that you can reach. But Google's interesting because they are measuring this PUE in the facilities that they own, which is around 20 to 25 data centers where they've specifically designed them. They've built them, they own the facilities and they own all the equipment, but they actually use hundreds of facilities around the world that they don't own. They lease them or they rent space for a certain amount of equipment that they deploy there, and they don't report those numbers. Arguably, they don't control them, so they shouldn't have to report them, but also arguably it's a nice way to hide those facility numbers that are perhaps not as efficient. And then power distribution is also quite interesting because of the losses that are involved in getting power from the distribution from the utility into the facility itself. This slide is quite old, it's over 10 years old, but it was published by Amazon showing the various stages of how electricity goes through one of their data centers. And you can see these different steps. There's the generator, there's the storage of the electricity in batteries, those batteries tend to provide minutes of storage. And the idea is if the grid goes down, the batteries take over for a few minutes whilst the generator starts, and then it switches over to the generator power until the grid returns. But you can see that there are losses at each stage, even as it gets to the IT load, and about 11% power loss, which you can relate to that 1.10 PUE from Google. They're very efficient. They managed to reduce those losses, but there are still losses just in operating a facility doing nothing because of the power distribution. So the common question then is, well, how much energy do data centers consume? And there's two main positions on this. The first one is it's about 1% of global demand, which is about 20,000 terawatt hours a year globally, increasing, but this is from 2018. And the value is fairly flat. It has increased a little bit since 2010, but not that much. This is the position taken by researchers from the Lawrence Berkeley National Laboratory in the US, and is supported by the large hyperscale providers, Google, Amazon, Microsoft. This suggests that 200 terawatt hours a year of electricity is involved globally, and that growth has plateaued. And this is a graph from a paper in Science last year, which shows the breakdown, the same breakdown that I've just gone through in terms of servers, storage, network, and infrastructure. And they also break out by the different types of data centers. They are talking about three different types: traditional data centers, which are very old facilities that generally are not very efficient. And those are more the ones that are represented on that industry graph that I showed you of the PUE. And then hyperscale in 2010 was a very small proportion, but as we're getting into 2018, that's significantly more. And then cloud is somewhere in between. These are the providers that operate kind of at mid to high scale, but not as large as the likes of Amazon and Google. And the key thing to note from this is that although energy consumption has not really increased that much, the demand for compute instances, networking, and storage has increased significantly since 2010. And the number of instances, which might be virtual machines, could also be physical servers, has more than doubled over the last decade or thereabouts. But despite that, energy consumption has plateaued. And the underlying reason for this in this model is to do with the migration from those traditional data centers, which are not very efficient, over to hyperscale and cloud, which is much more efficient. The other position is one taken by the mainstream media and certain other advocacy groups, that data center electricity usage is absolutely massive and is growing almost exponentially. The values from here are, when they project out into the future, an order of magnitude higher than the other position. But for 2018, rather than 200 terawatt hours, the estimates here are 600 terawatt hours a year, and that is expected to grow even in the best case scenario to 2030, where energy efficiencies are continuing as we've seen in the past. And the three different scenarios on this graph, presented in a paper a couple of years ago, suggests that the worst case scenario, it's almost 30% of global electricity demand is going to be taken up just by data centers by 2030. The authors of this paper have published a number of subsequent papers which changed these estimates somewhat. They reduced them slightly, but not sufficient enough to change their position generally, that it's more than an order of magnitude larger to be expected. And when you dig into the methodology behind these papers, there are a number of issues. The main one is that it just extrapolates from past growth into the future without really understanding how efficiency change, and without doing any real original work on the modeling, collecting of numbers. And so I'm personally highly skeptical of this 7.9 terawatt hours of growth over the next 7 to 8 years. We'll come back to that just a minute. Now, so far I've been talking about energy, and my most recent work, including a report that's coming out in a month or so from the Uptime Institute, is on data center water. And whilst the IT industry has made significant improvements in terms of energy efficiency, but also moved to renewable electricity, water consumption generally doesn't get any attention. It's only in the last few months that some mainstream media outlets have started investigating this in more depth. And there are two main ways that water is consumed in the data center. The first one is on-site consumption, which is what most people think about when they think about the water consumption of a data center, and that's the cooling. Water is used to cool down the air that is recirculated within the data center. There are several different mechanisms for how this works, whether it's direct air cooling, evaporative cooling, spraying water into the air and then blowing the hot air over the cooling water. But this is direct consumption by the data center, where there is a meter in the data center and you can see the consumption ticking over. And where water is reported, as this by Microsoft and Google, this is what they're talking about, so the direct consumption. But as you can see from this graph, there's actually significantly more water consumed indirectly as a result of electricity generation. And that's because the majority of electricity globally is still generated by fossil fuels. And the majority of that is through the evaporation of water to turn a turbine, which generates the electricity. And this is what water is consumed when you're using gas-powered, coal-powered power plants, and then separately hydropower as well. There's still water consumption there, often from evaporation from the reservoir, but also water just going through generators and potentially going on to downstream users or being recirculated. The reason this is important is because the context of the data center and its location is relevant to understanding water consumption. You might have a recirculation system within the data center that allows you to withdraw a small amount of water locally. But if you don't take into consideration the water that's consumed by the electricity generation, you can claim that your data center is very efficient from the direct consumption, but it can still be placing a lot of stress on the local water ecosystem, whether that's the actual ecosystem in terms of the animals and the other parts of the ecosystem that you might would be drawing water from. Water stress is a particular challenge, certainly in Africa and other dry regions, which are going to see all of the growth in data centers in the future. But even in the US, there are regions that have significant water stress, and data centers tend to draw large volumes of water directly, and as does power generation, and they can be some of the largest consumers of water in a particular region. Coming on to cloud computing, this is an industry that we've seen grow pretty significantly over the last decade. And the hyperscale providers, Amazon, Google, and Microsoft, are essentially the only ones that matter because they operate at such a scale that they can justify activities such as building their own servers and their own processors custom to specific workloads, whether that's Amazon with its custom Graviton ARM chips, or Google with its tensor processing units for machine learning. All of these contribute to improving energy efficiency and are a big reason for the improvements in efficiency in that first model, where we're assuming that energy consumption is flat over the last 10 years, just because hyperscale is able to be significantly more efficient. Now, comparing these three providers is particularly challenging because they have varying degrees of transparency with their environmental reporting. Now, Google is certainly the best at this. They're the most transparent. They publish PUE and their carbon intensity figures, either annually or on a quarterly basis. But this is generally globally rather than specific to certain regions. And Google has also been carbon neutral since 2007. and matched its energy usage with purchases of 100% renewable energy in 2017, and has done so every year since. Microsoft has also been carbon neutral since 2012 and has a goal of powering all of its operations with 100% renewable energy by 2030. But it doesn't publish PUE or carbon intensity. And Amazon, unfortunately, the largest and least transparent, publishes no environmental data other than their total carbon footprint for the company as a whole. And because Amazon's footprint is primarily from its logistics operations rather than Amazon Web Services, you can't really compare them. It's not a fair comparison because Google and Microsoft don't have all of the shopping sites globally. Amazon's also only published its power mix average carbon intensity once in 2015. And this is proving a challenge when you're trying to compare and understand which cloud provider is better and on what measure. Further to that, there are 3 separate definitions that you have to understand when making a comparison, when understanding the sources of energy and what carbon neutral means versus what renewables matching means. Because when a data center operator says they use 100% renewable electricity, they don't actually use 100% renewable electricity because it's impossible to do that on a 24/7 basis in almost every region. Carbon neutral is the first step, and that's where Google has been for over a decade and Microsoft for the last few years. That essentially means you offset your emissions by buying the offsets. You pay someone else to either not emit or to withdraw those emissions from the atmosphere in some way so that you as an organization can continue to emit. The second thing is renewables matching. And this is the purchase of generally renewable energy certificates or RECs. But in the case of the big 3, they're also purchasing power purchase agreements for renewables. So they can match 100% of electricity that they consume with 100% renewable electricity generated somewhere else in the world. Not necessarily where they actually consumed it, but when you compare them on an annual basis, they match up 100%. And then 100% renewables is only consuming renewable energy on the local grid. So that every single electron that goes into the data center has been generated from a renewable source. Now, Google's been making the most progress on this. And they publish these really nice graphs, which show, in this case, a theoretical data center that would be consuming electricity generated from renewable sources 100% of the time. What is actually happening is that, in this case, this is Finland, they're not able to match 100%. In January, 96%, November, 82%. Sometimes they hit 100%, but not always. And then a data center in the US, it's a worse position. And this is because renewables are variable. If we look at this graph, which I took yesterday from Electric Insights, which is a free website that aggregates the electricity demand and sources of power in the UK, you can see these graphs. You can see the yellow and the blue. It's wind and solar. These are changing. You can zoom right down to a daily level. This is zoomed out for a six-month period for this year, and you can see how this is changing throughout the day because we have no control over the sun and no control over the wind, and so we have to make up the gap with other sources. Currently, a lot of gas here, a minimal amount of coal. You can see nuclear provides the baseline, and then there's some pumped storage and imports from Europe as well. And each country, each region has its own version of this that will tie into weather conditions and the local availability of different types of generation. And so when we say 100% renewable 24/7, this graph would be completely wind and solar, maybe hydro as well. And I consider nuclear renewable as well. It would essentially remove the gas and coal, and then maybe imports and exports, depending on where it's coming from. But there's no region in the world that is able to do that. and certainly no region where there are major data centers. Arguably, Norway and potentially Iceland are able to achieve this, but there are no major data centers in those regions. And so what you get is something like this chart, which shows all of Google's data centers, actually all of their different cloud regions. And you can see the percentage, what they call carbon-free energy or electricity percentage, depending on the location. And then because they are drawing from the grid generally, you can see also the grid carbon intensity, and that varies quite significantly by region. Now, because Google is carbon neutral, the net carbon emissions are 0, but publishing this number allows customers to make a decision about where they might be placing their workloads. Unfortunately, they only provide this on an annual basis, and it's actually almost 18 months delayed when they release it. So this is a good first step, certainly, having this breakdown by region, but it doesn't allow you to dynamically move your workloads around to, let's say, choose the lowest carbon grid intensity over the next couple of hours. You couldn't move your workloads. You could make some assumptions as a Google Cloud customer, but I would expect that to change because Google is doing this internally. They do things like move the YouTube encoding to regions based on where the most renewable energy is available, because unlike a Google search, which has to return within a couple of milliseconds, encoding a video, if you wait an extra 20 minutes, it doesn't really matter. And so they can move those workloads around. But this is very challenging to do. You have to have the right architecture, you have to have the right software, and you need the data. And most environments just don't have that available yet. So to summarize, 1 to 2% of global electricity usage. When you see wild claims in the media about 2%, up to 30% of electricity over the next couple of years being used by data centers, you should certainly question that. It's generally based on extrapolation rather than original research. 1% is potentially too low. There is a question around whether crypto generation, certainly Bitcoin and Ethereum mining, whether that is included in the estimates or not. And also there's a challenge of transparency. There are some figures showing that China just alone uses 200 terawatt hours for its data centers, which if that's the case, that is double the supposed global estimate of the first group that I was talking about. But going up to 600 to 1,000 terawatt hours a year is certainly too high. So it's, I think my personal view is that it's somewhere in between if you account for crypto, somewhere between 1 and 1.5% global electricity usage for data centers. Second point is that cloud is growing massively. It's where most new workloads are deployed, certainly, and it's very efficient. So it is certainly more energy efficient than running your own servers in your own data centers. That's true as a generalization, but there are certain scenarios where that might not be accurate. So if you have the ability to maximize your utilization of servers, and certainly in machine learning and data mining or processing, you can optimize the workloads by having highly efficient software, scheduling workloads really well, and also having dedicated hardware specifically for those workloads. But generally, the cloud is the best place to put workloads, whichever cloud it is. And then finally, 100% renewable doesn't actually mean that. And it's going to take time and a lot of investment from the different cloud providers and data center operators generally to be able to reach that, because the whole purpose of a data center is to provide reliable power and internet access and cooling to IT workloads. And if renewable electricity is not available, you can't just switch those workloads off. So what we're starting to see now over the last couple of years is large high density storage being deployed alongside renewable generation. So in this final picture, you can see a Google data center here. They've got a nice solar array there. Can't see any batteries in this picture, but they have commissioned data centers where the battery capacity is almost matching the the generation capacity of the solar energy so that it can be charging those batteries, long-term storage, so that they can make up the difference when renewables are not available on the grid. Thank you very much.
Yes, thank you, David. At least for me, that was quite some new information. I hope there are some questions in the chat, or at least there are a few. Who was this with his hand? Jan.
Hi.
Hello, Jan, please.
Thanks, David, for this very nice talk. I'm at an astronomy institute, and we were assessing our climate impact. And we always thought that because we are going to observe in Chile and stuff, that our flights are using most of CO2. But when we turn to our computing needs, then indeed our computing is the most CO2 intense. It is about 5 tons of CO2 per astronomer per year, and probably double that number if we actually use the German grid and not the electricity mix that our city provider is giving us. So, and I was wondering, you said that there are no major data centers in Norway or Iceland. Do you know where the whole thing is going to, or why are there no data centers there? Because that would be for me the first thing to go there and plant my hyperscale centers into those places.
Yes, thanks for the question. So when I say major data centers, I'm talking about the hyperscaler regions. There are certainly data centers in those countries, but it just depends on who's owning them and how they make those resources available. The challenge that you have when you're placing a data center is there are a number of competing characteristics that you're looking for. You're certainly looking for cheap land. That tends to be the most important aspect to build the data center. You want access to people who can firstly build the data center, but then operate it. And you need access, or you need good access to the electricity grid. And the national grid operators for Ireland and Denmark have talked about how almost 100% of their growth in demand over the next decade is going to come from data centers. And this can be challenging for the local grid. But the other aspect is latency, which is how long it takes to get a response from any workloads that are running in those data centers. And this has a real impact on the user experience for applications. If it takes an extra 500 milliseconds to load a website, you might not notice. But if you are placing a bet on a sporting event and you are 500 milliseconds out, the bet may have closed by the time you've made your decision and placed the bet. Or equally, if you're doing financial trading, you need to be making decisions within single-digit milliseconds. So it really depends on the workload about where you can place the data center. And certainly Google, one of the pictures I included is of Google's data center in Finland, which is in the far north, where they have access to a lake that has very cold water. And so they have no issues with the cooling, but that data center is in the middle of nowhere. And so if you're going to place workloads there, that may be perfectly acceptable and you get the benefits of the lower environmental impacts, but you might have to accept higher latency and higher response times for your application.
Okay, thanks.
Melissa had a question. She put it in the chat, and it's actually the same question I had. I mean, I'm also quite surprised that the numbers didn't grow that much, while all the internet is obviously growing that much. But probably this COVID lockdowns changed these numbers quite a bit. I mean, we are all now meeting in Zoom. That's all not in your numbers. Do you think that will have a long-term impact on this whole numbers?
The initial lockdowns last year are an interesting case study because the internet providers reported up to 50% increase in internet traffic almost overnight in some locations, and certainly over the period of a few days to a week. But they've also all reported no growth in energy consumption. And although the data is still new, and I think there's still some analysis to be done on that, there are a couple of reasons. The first is that capacity is deployed to cover peak load, which only occurs at a very small time during the day. And even then there's overhead to be able to deal with that. So the capacity is already deployed and already in use. And we see these networks actually running at 15% utilization, 15 to 30% most of the time. Sometimes they increase, but it almost never goes over 50%, because if it did and there was a failure, then the network would suddenly be running at very low capacity. So the already deployed equipment was able to absorb that workload without any increase in energy. There is a degree of energy proportionality. So as workloads increase and network traffic increases, then the total amount of energy consumed will increase slightly, but it's not directly correlated depending on the workload. And so we didn't really see any increase as a result of COVID. Whether that maintains its trend is a separate question, because if workloads have increased and there was capacity to deal with that, it's likely that the network providers will over time add more capacity because they've hit a new normal, and so they need to build in that additional overhead. So it remains to be seen whether we can say there was no energy increase as a result of COVID. Just depends on what time window you're looking at.
Yeah, makes sense. Anyway, tricky. I mean, otherwise people stayed at home and didn't use the cars to go to work. But I just know for the University of Vienna, they invested quite a lot into servers last April. And they will probably stay. Lauren had another question. You asked your personal opinion on if this efficiency matrix will improve further, or so that, and if so, would that come to economical brackets, energy becoming more expensive, sociality from clients, or regulatory incentives? I hope you can read the question.
So the answer to this is a carbon tax, isn't it? That's the simple way of putting the externalities into the actual cost for anyone who's consuming anything that generates emissions. The problem with that is that nobody wants to pay more, certainly not consumers. They don't want to pay more. And then there's some challenges around, or can they afford to do that? Those costs are just going to be passed on by the companies to their consumers. And so I think there is a real challenge in just using a carbon tax as the simplistic answer. Potentially what we will see is more of the cap and trade systems. Europe certainly has one, and hopefully the UK will be implementing the same thing, because we were part of that scheme whilst we were in the EU. China has a cap and trade system as well. And that allows emissions to be moved around and to gradually reduce the ceiling of what you allow. The EU has done a really good job on efficiency specifically of the electrical equipment. A lot of the standards over the last 15 years have resulted in major improvements in the energy efficiency of light bulbs, computers, TVs, all those kind of things, those equipment that you just buy and use at home. Comparing a laptop today, a server today, a light bulb today from one that you might have bought 20 years ago, the efficiency improvements are significant. So I think we are seeing some regulatory pressure. The challenge with the cloud today is that it's almost impossible to make comparisons, because the operators are not publishing the metrics you need to do that. And so I think that's, if I had the ability to implement regulation, that would be the first thing I would do, is to make everything more transparent and then see what happened and see if businesses and consumers actually made decisions based on that data. But until we have the transparency and the consistency in the reporting, it's very difficult to make a decision on which provider you should use.
Thank you. There's another question of Andrew. He's also thanking you very much for your talk. And what are the key decisions we can make as higher education institutions to reduce our emissions from IT?
generally moving workloads to cloud providers is the best step. Certainly for general workloads like running email, document storage, those kind of things, that it doesn't make sense for institutions to run themselves. Most of the time I see institutions using Office 365, Microsoft's cloud product, and the scale that they're able to operate those at means that when they are making investments, which they are in efficiency and being carbon neutral and reducing their water footprint, then all of their customers automatically get that for free. You don't have to do anything. The challenge comes for the specialist workloads, and potentially with that astronomy example, a large part of that is the huge amount of data that is collected that needs to be stored somewhere and potentially transferred to different processing environments. And if you have those huge volumes of data, it can be very expensive to store it in the cloud if you're not careful. So the specialist workloads may make sense to run locally, but I would say generally moving to one of the cloud providers is the best step.
So with other words, it would make sense if I store data in the cloud I probably do not need in the future anymore to just delete this, huh? So it's...
well, it depends. If you're storing it on your computer locally, you've already purchased that storage, so that you've already got the emissions from the manufacturing of the equipment. And when it comes to personal devices, the majority of the carbon footprint of the device is in the manufacturing. For servers, the majority of the carbon footprint is in the usage of that equipment. So it depends where it's being deleted from. Deleted from your laptop, it doesn't really make any difference. If it's deleted from a server, if that's a physical server in a data center you operate and you're able to retire it, then that's a good step. But if you're moving it to the cloud, that storage already exists and is growing significantly. And probably the efficiency improvements of the power draw of the disks is falling faster than you can delete the data. So it probably doesn't make any difference.
Thank you. Are there any more questions in the forum? I would say thank you very much again, David. It was very interesting. I will think about this next time when I use computers, and all the best, huh?
Thank you.
Have a great afternoon, everybody. Goodbye.
Bye.